Out there, right now, in the profound and silent blackness between worlds, a lone spacecraft is holding a perfect course. It is billions of miles from the warm, bustling control rooms of Earth, utterly isolated in the freezing vacuum. There is no pilot at the controls, no human hand on the joystick to make a quick correction. Yet, this probe, a tiny speck of human ingenuity, is navigating the most complex and hazardous environment imaginable with an elegance that borders on artistry. It's a thought that should give you pause. How is such a feat even possible? How can a machine, built on our world, operate with such flawless precision in a realm so alien and vast that the very concept of distance loses all familiar meaning? The answer is not found in a single, powerful engine or a massive onboard computer, but in something far more subtle, far more beautiful. It is guided by a series of hidden rhythms, a silent, continuous symphony playing out in the void. These are not rhythms you can hear, but they are the very heartbeat of deep space exploration. They are the unwavering pulse of an atomic clock, counting out nanoseconds with staggering precision. The predictable, gravitational dance of planets swinging through their orbits, and the constant, silent gaze of star trackers locking onto the fixed lights of the cosmos. This is a symphony composed of physics and computation, a delicate interplay of internal timers and external cues that allows a robotic explorer to maintain its alignment, its trajectory, and its purpose across years and even decades of solitary travel. It's a system of cosmic synchronizations so refined that it can thread a needle billions of miles away, flying through a gravitational keyhole with an accuracy that defies belief. This is the hidden architecture of autonomy, the invisible framework that makes our grandest voyages of discovery not just possible but routine. In this video, we are going to pull back the curtain on this extraordinary process. We will unravel the mysteries of these guiding pulses, exploring the fundamental principles that allow a probe to essentially think for itself, to correct its own course, to manage its own energy, and to keep its instruments perfectly pointed while its human creators are separated from it by a communication delay that stretches for hours. We will delve into the science of celestial timing, the elegant algorithms of self-correction, and the future of navigation that will one day take us to other stars. This is a journey into the silent, intelligent core of our farthest-reaching robotic ambassadors, a look at the meticulous planning and brilliant engineering that turns a collection of metal, wire, and silicon into a resilient, thinking explorer. So prepare to discover the silent pulses, the hidden rhythms that orchestrate humanity's most ambitious journeys into the great unknown. To truly grasp the scale of this challenge, consider what it means for a signal to take over 21 hours for a simple round trip. A command sent from Mission Control in California, a simple instruction like "Fire thruster number 2 for 1 second," would travel at the speed of light for an entire day just to reach Voyager. The probe would then receive the command, execute it, and a confirmation signal would begin the 21-hour journey back. By the time engineers on Earth saw that confirmation, more than 42 hours would have passed. Now imagine an emergency, like a sudden pressure drop in a fuel line or an unexpected course deviation. By the time anyone on Earth even became aware of the problem, the spacecraft could be lost forever. This is not like remotely piloting a drone over a battlefield. It is more like sending a letter via sailing ship across an ocean and hoping your instructions are still relevant when it arrives months later. This fundamental physical limitation of the speed of light is the ultimate governor on deep space missions, forcing us to abandon the very idea of direct, real-time control. The spacecraft must be its own captain, its own engineer, and its own navigator, capable of diagnosing problems and executing complex sequences entirely on its own. This level of self-reliance requires a profound shift in design philosophy. Instead of a remote-controlled robot, we are building an artificial explorer, imbued with a kind of robotic intelligence and foresight. It must carry within itself not just the tools for its mission, but the knowledge and the decision-making frameworks to use those tools correctly, millions of miles from any help. This is where the concept of hidden rhythms becomes so critical. These rhythms are the foundational elements of this robotic independence. They are the pre-established patterns and predictable cycles that the spacecraft can use to orient itself, to keep time, and to make decisions. Think of it as teaching the probe the basic steps of a dance before it leaves Earth. It learns the rhythm of planetary orbits, the steady beat of its internal clock, and the choreography of its own flight path. Once it's out there, it doesn't need us to call out the steps. It just listens to the music of the spheres and dances on, perfectly in time, all by itself. This system of internal and external cues creates a stable, predictable environment for the probe to operate within, even when its external environment is the chaotic and vast expanse of interstellar space. The vastness of space itself is the other half of this grand challenge. We are not just sending probes across a large, empty volume. We are launching them into a dynamic and complex gravitational symphony. The Sun's gravity is the dominant force, but every planet, every moon, every large asteroid exerts its own tiny, persistent pull. Over a journey of billions of miles, these minuscule tugs can accumulate, slowly but surely pushing a probe off its intended path. A deviation of just a few millimeters per second, if left uncorrected for years, can result in missing a planetary target by hundreds of thousands of miles. Furthermore, space is not a perfect vacuum. There is the solar wind, a constant stream of particles from the Sun, which exerts a tiny but continuous pressure on the spacecraft. There is the subtle, uneven effect of the spacecraft's own heat radiating from its surfaces, which can impart a tiny thrust. These are forces so small they are almost impossible to measure on Earth, but over the epic durations of a deep space mission, they become significant navigational concerns. The probe must therefore be built not just for autonomy, but for incredible precision and stability. It must be able to sense these infinitesimal drifts and have the capability to make equally tiny, precise corrections. This demands a new paradigm of guidance, moving from the model of a human driver constantly turning a steering wheel to that of a master clockmaker, creating a mechanism of such perfect balance and internal harmony that it can keep accurate time for centuries. The solutions we've developed are a breathtaking blend of the simple and the sublime, from the unwavering vibration of cesium atoms to the ancient, fixed positions of the stars. Understanding this immense challenge is the essential first step, because it frames every piece of technology and every line of code that follows not as mere engineering, but as a necessary answer to one of the most difficult problems we have ever faced: how to extend our presence and our curiosity across a universe that is fundamentally and unforgivingly vast. But what does that internal tempo actually sound like? It's not the familiar tick of a grandfather clock or the digital readout on your phone. It is a vibration, an oscillation, happening at a frequency so high and so stable it defies human comprehension. Inside an atomic clock, atoms, often cesium or rubidium, are excited by microwaves. Scientists tune these microwaves to the exact frequency that causes the atoms to change energy states, a transition that is incredibly regular and predictable. This atomic resonance becomes the pendulum of the clock, a pendulum that swings not once per second, but over 9 billion times each second for a cesium atom. This is the unerring pulse that lies at the heart of the probe. It is this staggering precision that transforms time from a simple measurement into the foundational grid upon which all navigation is plotted. Think of it this way: when you're trying to figure out where you are on Earth using GPS, your phone is comparing the timestamps from multiple satellites. A timing error of just 1/1,000,000th of a second would translate into a positioning error of over 1,000 feet. Now scale that up to the solar system. A probe determining its position by bouncing a radio signal off a planet and timing its return absolutely must know, with near-perfect accuracy, exactly when that signal left and when it came back. A timing error of just 1 second could mean a miscalculation of its position by the actual distance light travels in that second, over 186,000 miles. The atomic clock eliminates this vulnerability. It provides a constant, stable heartbeat against which the probe can measure the Doppler shift in its communications signal with Earth, the subtle stretching or compressing of the radio waves caused by the spacecraft's motion, to calculate its speed with breathtaking accuracy. It allows the onboard computer to schedule a critical engine burn to the exact millisecond, ensuring the thrust is applied in the perfect direction for the perfect duration. Without this rock-solid internal rhythm, the probe would be like a musician trying to play a complex symphony without a conductor or a metronome, with each instrument slowly drifting out of sync until the entire piece descends into chaos. The atomic clock is that conductor keeping the violin of the star trackers, the cello of the gyroscopes, and the trumpet of the thrusters all playing in perfect, harmonious time. It is the first and most non-negotiable rhythm, the master timekeeper for a journey where a single missed beat could mean missing a world. With that internal metronome ticking away flawlessly, the probe is ready to move. But it doesn't simply aim its engines at a distant planet and blast away. That would be like trying to swim directly across a powerful, swirling river by pointing at the opposite bank. The current would sweep you far downstream. The solar system is that river, and its currents are gravity. This brings us to the second fundamental rhythm, a grand and external one, the celestial dance of orbital mechanics. Our solar system is anything but a static collection of points of light. It is a dynamic, complex, and beautifully predictable ballet of gravitational forces, with every single body, from the mighty sun to the smallest asteroid, constantly pulling on every other. A spacecraft launched from Earth is immediately a participant in this dance, caught in the sun's powerful gravitational embrace. Its path is not a straight line but a curve, an orbit. To get anywhere, it must work with these forces, not against them. The most brilliant example of this is the gravity assist or slingshot maneuver. Think of it as a form of cosmic theft. As a probe flies close behind a moving planet like Jupiter, the planet's immense gravity pulls the spacecraft forward, accelerating it. The probe steals a tiny, almost imperceptible bit of the planet's own orbital momentum. From Jupiter's perspective, the effect is negligible, like a speeding train not noticing a fly landing on it. But for the probe, the boost in speed is monumental, saving years of travel time and enormous amounts of precious fuel. The Voyager probes used a once-in-176-year alignment of the outer planets to perform a grand tour, using each successive world as a gravitational stepping stone to fling them further out into the void. This isn't random luck, it's choreography. The rules of this dance were written centuries ago by minds like Johannes Kepler and Isaac Newton. Kepler's laws describe how planets move in ellipses around the sun, speeding up when they are closer and slowing down when they are farther away. Newton's law of universal gravitation gave us the mathematical language to calculate the exact force of that pull. Together, these principles form the predictable rhythm of the heavens. Years before a probe like Cassini or New Horizons even leaves the launch pad, navigators and mathematicians on Earth are using supercomputers to play out this celestial dance millions of times. They calculate the perfect trajectory, a precise, pre-composed score that tells the probe exactly where it needs to be at every single moment of its journey. This flight path is in itself a rhythm, a scheduled sequence of positions and velocities, a timeline of celestial events. The probe's job is to constantly listen to this external rhythm and ensure it is in step. Its onboard systems use their star trackers and radio signals from Earth to determine its actual position and speed, and then they compare this reality to the pre-loaded celestial score. Is it a fraction of a millimeter per second too fast? Is it a few kilometers off to the side? This continuous process of checking and comparing is what keeps the spacecraft locked into the gravitational highway. It's not fighting the currents of space, it is riding them with expert precision, ensuring it arrives at the exact right point in space at the exact right cosmic moment to receive its next gravitational push or to begin its orbital insertion. This external rhythm, the grand clockwork motion of the solar system, provides the very pathway upon which the entire journey depends. Yet, with a perfect sense of time and a pre-charted course through the gravitational flows, our probe still faces a fundamental problem. How does it know which way it's facing? In the absolute blackness between worlds, there are no road signs, no horizon, no up or down. A spacecraft could be slowly tumbling end over end and have no intuitive sense of its own rotation. This is where the third rhythm comes into play, a guiding beacon drawn from the most ancient of human navigation tools, the stars themselves. Locked onto the steady, unchanging positions of distant suns, the probe establishes an unwavering sense of attitude, its orientation in the three-dimensional void. It accomplishes this feat with a remarkable piece of technology called a star tracker. Think of it as a supremely intelligent, automated sextant. This isn't a simple camera. It's a highly sensitive optical device that continuously images the star field around the spacecraft. But it doesn't just take a pretty picture. Its onboard processor immediately gets to work, identifying the patterns of bright dots in its view. It then compares this live star map to a built-in catalog, a digital almanac of the sky's brightest and most reliably positioned stars. By matching the observed pattern to the catalog, the star tracker can calculate with extraordinary precision exactly which direction the spacecraft is pointing at that very instant. This is a continuous, rhythmic process of observation, pattern recognition, and confirmation. It's a feedback loop that runs dozens of times per second, a constant whisper of spatial awareness in the crushing silence of space. This stellar rhythm is what keeps the entire mission grounded. It ensures that the probe's high-gain antenna, its lifeline to Earth, remains pointed accurately at our tiny, distant planet. Even a slight misalignment over billions of miles would mean the radio signal missing Earth entirely, severing the communication link and effectively ending the mission. Simultaneously, this stable orientation is crucial for science. A probe like the James Webb Space Telescope relies on this stellar reference to hold its gaze fixed on a single galaxy for days on end, collecting photons that have traveled for billions of years. A camera on a Mars orbiter uses this knowledge to point its lens straight down at the Martian surface as it speeds over it at thousands of miles per hour. Without the constant, corrective rhythm of the star trackers, the spacecraft would be lost, its instruments staring uselessly into empty space instead of gathering priceless data. The beauty of this system lies in its elegant simplicity and profound reliability. The stars used for reference are so immensely far away that their apparent positions are effectively fixed for the duration of any spacecraft's mission. They are the only truly stationary landmarks in a cosmos of constant motion. While planets whirl around the sun and moons dance around their planets, these distant suns provide a fixed backdrop, a celestial grid against which the probe can always recalibrate its sense of self. This rhythm of stellar reference is therefore a dialogue with permanence, a way for our fleeting, human-made machine to anchor itself against the immutable architecture of the universe. It transforms the spacecraft from a passive piece of driftwood tossed on the gravitational seas into an active, oriented navigator capable of holding its course and its focus across the light years. So we have these distinct, vital rhythms playing simultaneously: the unwavering tempo of the atomic clock, the celestial pitch of the star trackers, and the gravitational score of the orbital path. But a collection of individual musicians, no matter how talented, does not make an orchestra. For that, you need a conductor, and in this cosmic symphony, that role is filled by the spacecraft's main computer, performing a continuous, brilliant process known as sensor fusion. This is the moment where all the disparate data streams are blended, compared, and synthesized into a single, coherent, and stunningly accurate picture of reality. It's the difference between hearing a violin play alone, a cello by itself, and a flute in isolation, versus hearing them all come together in a harmonious piece of music. The computer is not just listening to each instrument, it is understanding how they relate to one another, using the strengths of one to cover for the momentary weaknesses of another, creating a whole that is far greater than the sum of its parts. Think about how you navigate the world yourself. You don't rely solely on your eyes. You use your sense of balance from your inner ear, the feeling of the ground under your feet, and even sounds from your surroundings. If you close your eyes and stand on one foot, you might wobble because you've lost one crucial data stream. Your brain is a master of sensor fusion, constantly taking all these inputs and creating your stable perception of the world. A deep space probe does the exact same thing, but in an environment where a single wobble could mean disaster. Let's meet the key players in this ensemble. The atomic clock, as we've discussed, is the impeccable metronome providing the fundamental tick of time. The star trackers are the virtuoso violinists, reading the sheet music of the cosmos to provide an absolute, external reference for orientation. But they have a limitation. If the spacecraft rotates too quickly, the star tracker's image can blur, making it temporarily useless. This is where the gyroscopes come in. These are the orchestra's cellos, providing a rich, internal sense of motion. A gyroscope is a spinning wheel mounted in a set of gimbals that allow it to maintain its orientation in space due to the conservation of angular momentum. When the spacecraft rotates, the gyroscopes resist that motion, and by measuring the forces required to keep them stable, the computer can detect every tiny twist, turn, and roll. Gyroscopes provide incredibly precise data on rotational changes, but they have a flaw called drift. Over time, tiny imperfections and friction cause their sense of straight ahead to slowly, imperceptibly wander. So you have the star tracker, which is absolutely accurate but can be temporarily blinded by fast motion, and the gyroscope, which is always active and responsive but gradually drifts off course. Sensor fusion is the genius that marries these two. The computer uses the star tracker's occasional, rock-solid absolute fixes to correct for the gyroscope's slow, accumulating drift. It's a continuous calibration, a conversation where one instrument says, "I feel like we're turning," and the other periodically chimes in to confirm, "Yes, we are, and here is exactly how much we've turned relative to the universe." Then there are the sun sensors, often the unsung heroes of the ensemble. These are simpler, more robust devices that act like a basic compass, telling the spacecraft where the sun is. They may not have the pinpoint accuracy of a star tracker, but they are almost impossible to fool and provide a crucial backup reference. If the star tracker gets confused by a bright reflection from a nearby planet or needs to be reset, the sun sensor can quickly provide a rough orientation, enough to point the main antenna back toward Earth or to maneuver the spacecraft into a position where the star tracker can reacquire its bearings. The computer fuses this solar data into its overall model, using it as a sanity check. If the gyroscopes and star trackers are disagreeing wildly, a quick glance at the sun sensor can help the computer figure out which sensor is having a bad day. This process is managed by a sophisticated mathematical algorithm, most commonly a Kalman filter. Think of the Kalman filter as the conductor's refined sense of rhythm and pitch. It doesn't just take each sensor reading at face value. It understands that every measurement has a little bit of noise, a little bit of uncertainty. So it constantly makes a prediction of the spacecraft state, where it should be and how it should be pointing based on its previous known state and the data from the gyroscopes. Then, when a new, noisy measurement comes in from the star tracker or sun sensor, the filter doesn't just replace its prediction with this new data. Instead, it performs a weighted average, blending the prediction with the measurement, trusting each one based on its known reliability. The result is a refined, smoothed, and incredibly accurate estimate that is far more trustworthy than any single sensor reading could ever be. This is the cognitive rhythm of the probe, a cycle of prediction and update that runs hundreds of times per second, smoothing out the jitters and glitches to create a crystal clear, stable perception of its own existence in the void. This integrated perception, this single state of awareness, is what transforms a passive collection of data into the capacity for intelligent, autonomous action. The computer now knows with high confidence its position, its velocity, and its orientation. It can now make a decision: is our current trajectory matching the pre-loaded celestial score? If not, it can calculate the exact thrust needed for a correction and command the thrusters to fire for a precise duration. It is this seamless synthesis of separate rhythms that elevates the machine from a mere instrument to a true explorer, capable of guiding itself through the dark. But for all its profound independence, the probe is not a hermit. It remains part of a larger team, and it maintains this connection through a carefully orchestrated rhythm of communication, a scheduled heartbeat that pulses across the solar system. This isn't a constant, open phone line. That would be impossibly wasteful of the spacecraft's limited power and would overwhelm the capacity of the deep space network, our planet's incredibly sensitive ear on the cosmos. Instead, the link operates in precisely timed windows, brief periods of intense conversation punctuating long stretches of silent, autonomous work. Think of it like a parent checking in with a child away at a distant summer camp, where letters are only sent and received on specific days of the week. Both parties know the schedule, and they live their lives accordingly, saving up their most important news for those designated moments of connection. For the probe, this rhythm is dictated by the relentless turn of the Earth and the probe's own motion through space. The giant, dish-shaped antennas of the deep space network, strategically placed in California, Spain, and Australia to ensure constant coverage as our planet rotates, can only point at one tiny patch of sky at a time. A communication window opens when the geometry is just right, when the specific antenna tasked with listening can actually see the spacecraft above its local horizon, and when the probe itself has its own antenna pointed accurately back at Earth. The spacecraft's computer, synchronized with its atomic clock, knows this schedule intimately. It carries a timeline that says, for example, at 1400 hours, 32 minutes, and 10 seconds mission elapsed time, point the high-gain antenna to coordinates X, Y, and Z, and begin transmitting the data stored in Memory Bank 7. This is its time to speak. It will power up its transmitter and pour out a compressed stream of everything it has learned and recorded since the last call home. Images of an alien moon, readings of magnetic fields, and a full report on its own engineering health. This downlink is a high-powered, focused shout into the void designed to push the maximum amount of data across an immense distance. Then the rhythm shifts. The probe falls silent and switches its receiver on. This is its time to listen. For a precious period, it waits, its electronic ears open for any new instructions from its human collaborators. These commands are not joystick movements. They are intricate, time-tagged sequences of code that will be stored onboard and executed later, according to the probe's internal timeline. A command sequence might tell it to execute a science observation in 3 weeks' time, or to adjust a thermostat setting, or to prepare for a major trajectory correction maneuver. This rhythmic cycle of planned solitude and intense connection is a masterclass in efficiency. It allows the probe to focus entirely on its mission, free from the distraction of constant chatter, while also ensuring that its human guides can provide strategic direction, upload new software, or respond to unexpected opportunities. The power saved by not transmitting continuously is enormous, directly translating into a longer operational life. This scheduled heartbeat is therefore more than just a technical necessity. It is the vital, rhythmic breath of the mission, the regular pulse that confirms the spacecraft is still alive, still thinking, and still exploring, binding our world to a tiny, intelligent machine as it voyages through the endless night. Even with a perfect flight plan and a flawless internal sense of time and direction, the path of a deep space probe is never truly static. It exists in a sea of infinitesimal forces, each one conspiring in its own tiny way to push the spacecraft off its intended course. Think of it like sailing a vast, calm ocean. There's no storm, no giant waves, but there is a persistent, gentle current, and there are countless tiny ripples. Over a journey of thousands of miles, if you never adjusted your rudder, those subtle pushes would slowly but surely carry you far from your destination. For a spacecraft, these currents and ripples are physical realities. There's the constant, gentle pressure of sunlight itself. Photons from the sun, while massless, carry momentum, and when they strike the spacecraft's large solar panels or sunshade, they impart a tiny, continuous push known as solar radiation pressure. Then there's the gravity of countless small asteroids and dust particles that were too small to be included in the detailed gravitational models of the solar system. Their combined influence is minuscule, but over months and years it is cumulative. Even the tiny thrust from outgassing, the release of molecules trapped in the spacecraft's materials as they warm in the sunlight, can act as a microscopic, unwanted engine. These forces are far too small for any human to notice on Earth, but in the frictionless environment of space, where there is no air resistance to slower drift, they become significant navigational concerns. A velocity error of just 1 centimeter per second, slower than a crawling baby if left uncorrected for a year, would result in the probe being over 300 kilometers off course. Over a multi-year mission to Jupiter, that error could balloon to thousands of kilometers, enough to miss a crucial moon flyby entirely. This is the reality of deep space travel. Perfection is not a starting condition, but a continuous process of maintenance. This is where the fifth rhythm comes into play, a powerful demonstration of the probe's hard-won independence, the autonomous correction maneuver. These are not panicked, emergency reactions to a sudden crisis. You don't wait for your car to drift into the next lane before you gently turn the steering wheel. You make small, almost subconscious adjustments to keep it centered. In the same way, a probe performs periodic trajectory correction maneuvers, or TCMS. These are pre-planned, rhythmic adjustments baked into the mission timeline from the very beginning. They represent a scheduled moment for the spacecraft to check in with itself, to assess its actual state against the perfect, pre-composed score of its flight path, and to make the necessary minor correction. The process is a brilliant display of robotic self-awareness. First, the probe enters a dedicated navigation mode, using its suite of sensors, the star trackers, for orientation, its radio link with Earth for precise ranging data, and its onboard clock. It spends hours or even days gathering data to pin down its position and velocity with excruciating accuracy. It's essentially asking itself, where am I really right now compared to where my flight plan says I should be? The spacecraft's computer then runs complex calculations, comparing its measured state vector to the intended one. The difference between these two states is the error, the drift that has accumulated since the last correction. The computer's job is to solve for the exact thrust needed to cancel out this error. This isn't just a simple matter of fire the engine for X seconds. It must calculate a thrust vector, a specific direction in three-dimensional space, and a specific duration. Which thruster or main engine should it fire? In what precise direction should the spacecraft be pointing when it does so? How long should the burn last to impart exactly the right change in velocity, down to a fraction of a millimeter per second? Once the solution is computed and cross-checked, the probe prepares for the execution. It might maneuver to point its main engine in the required direction, a slow, deliberate rotation commanded by its attitude control system. At the precisely calculated moment, synchronized by its atomic clock, the engine ignites. This isn't a dramatic, Hollywood-style blast of fire and fury. For most mid-course corrections, it's a remarkably gentle and brief burn, often lasting just a few seconds or even less. The force might be so subtle that it would be imperceptible to a human standing on the spacecraft. But in the weightless, frictionless void, that tiny nudge is enough. When the engine cuts off, the error has been cancelled. The probe is back on the ideal path, its celestial dance steps perfectly realigned with the music of the spheres. It then returns to its normal cruise mode, resuming its silent journey, knowing that it has successfully managed its own destiny once again. This rhythm of self-assessment and autonomous course correction is perhaps one of the most profound expressions of the probe's intelligence. It's not just following orders, it is actively participating in its own navigation, taking responsibility for the countless unmodeled details of the real solar system. Each successful TCM is a quiet victory, a testament to an engineering philosophy that understands the universe is a complex and slightly messy place, and that the only way to navigate it across billions of miles is to build a machine that can not only follow a map but also reliably and calmly correct its own course. Carrying its own perfect sense of time and a pre-charted course, a deep space probe possesses a remarkable kind of foresight, a predictive knowledge of the cosmos that would seem almost magical if it weren't so rigorously mathematical. This foresight is encoded in a digital almanac known as an Ephemeris. Think of it not as a simple map, but as a dynamic, cosmic timetable. It's a vast, pre-computed database stored in the probe's memory that contains the predicted future positions, not just of its final target, but of every major celestial body in the solar system, the Sun, all the planets, and their most significant moons. This is the crucial shift from a probe simply knowing its own location to understanding its place within a moving, living system. It doesn't just ask, "Where am I?" It constantly asks, "Where is everything else supposed to be right now?" This shared model of the solar system is the ultimate navigational tool, transforming the spacecraft from a passive traveler into an active participant in the celestial dance. The creation of an ephemeris is a monumental task of human intellect and computational power, a process that begins long before the spacecraft ever leaves the launch pad. Astronomers and orbital dynamicists draw upon centuries of observational data, from the painstaking records of Tycho Brahe to the precise laser ranging of the Moon from modern observatories. They feed this historical data, which captures the precise gravitational interplay of the solar system, into incredibly powerful supercomputers running models of celestial mechanics. These models simulate the gravitational pulls of every body on every other body, projecting their motions forward in time with breathtaking accuracy. The result is a digital prophecy, a table that lists the exact coordinates of, say, Jupiter's moon Io for every single second of the next 20 years. This file is then uploaded to the probe's computer, becoming its reference reality, the sheet music against which it will compare the actual symphony of the heavens. The rhythm this establishes for the spacecraft is one of continuous prediction and verification. The probe's onboard systems are constantly checking the real, observed universe against this predicted model. For instance, its cameras might observe Jupiter and its moons. It can measure the actual positions of these bodies and compare them to where the ephemeris says they should be at that precise mission-elapsed time. If the observation and the prediction match, it's a powerful confirmation that the probe's understanding of the solar system is correct, which in turn reinforces the accuracy of its own calculated position. This continuous cross-check is a form of celestial sanity checking, a way for the probe to validate its entire worldview. This predictive power unlocks some of the most sophisticated and scientifically rich activities a probe can perform. Consider the phenomenon of an occultation when a moon or a planet passes directly in front of a distant star. For a scientist on Earth, this is a rare and valuable event. For a probe with an ephemeris, it's a scheduled observation. The spacecraft knows weeks or months in advance that, for example, on a specific date and time, Saturn's moon Titan will occult the bright star Bellatrix. It can autonomously schedule its instruments to power up, point its cameras and spectrometers with precision, and capture the event. As Titan moves in front of the star, the subtle changes in the starlight filtering through the moon's hazy atmosphere can reveal incredible details about its composition, pressure, and temperature structure. Without the ephemeris to predict this event down to the second, the probe would likely miss this fleeting opportunity entirely. Similarly, the ephemeris is the master key to the gravity assist maneuver. The probe doesn't just aim for where a planet is, it aims for where the planet will be at the exact moment of its flyby, and it calculates its approach vector based on the planet's predicted velocity and gravitational field as detailed in the ephemeris. This allows it to steal that tiny bit of orbital energy with surgical precision, using the planet's own motion as a slingshot to fling it further into the solar system. The ephemeris makes the probe an expert in celestial timing, allowing it to be at the right place at the exact right moment to catch a gravitational wave or to witness a cosmic alignment. There's also a fascinating self-correcting aspect to this process. While the ephemeris is incredibly accurate, it is not perfect. The gravitational influence of unmodeled asteroids or subtle non-gravitational forces like the Yarkovsky effect, where a body's own heat radiation acts as a tiny thruster, can cause very slight deviations over time. A sophisticated probe can actually detect these tiny discrepancies. If its observations consistently show that Jupiter is a few dozen kilometers away from its predicted position in the Ephemeris, this isn't treated as a failure. It's treated as new data. The spacecraft can report this deviation back to Earth, where navigators can use it to refine and update the master Ephemeris model. In some advanced concepts for future fully autonomous navigation, the probe might even use these discrepancies to update its own internal copy of the Ephemeris, slowly adjusting its model of the solar system based on its own direct observations. This transforms the rhythm from simple verification into a learning loop, where the probe doesn't just follow the cosmic timetable, but actively helps to write it, contributing its unique vantage point from the outer solar system to humanity's collective understanding of our celestial neighborhood. This shared, evolving model is what allows a machine built on a single planet to navigate with confidence through a system of worlds, its path guided by a digital oracle that contains the predicted future of the heavens themselves. Now consider the lifeblood of this entire autonomous system: electrical power. A deep space probe is an island, utterly isolated, and it must generate and manage every single watt of energy it consumes. There are no power outlets between planets, no service stations for a recharge. This reality imposes a sixth, absolutely critical rhythm upon the spacecraft's existence: the power management cycle. This is a meticulous, unending dance of energy allocation, a constant balancing act between the desire to do groundbreaking science and the absolute necessity of long-term survival. The probe's power budget is dictated by its source. For missions in the inner solar system, this typically means expansive solar panels, converting the sun's photons into electricity. But as a probe travels to the outer planets, sunlight becomes incredibly faint. At Jupiter, the sun is only 1/25th as bright as it is at Earth. At Saturn, it's only 1/100th. For these distant voyages, we turn to a remarkable technology called a radioisotope thermoelectric generator, or RTG. An RTG has no moving parts. It contains a pellet of a radioactive material like plutonium-238, which naturally decays and releases heat. This heat is then converted directly into electricity through solid-state thermocouples. It's a simple, rugged, and incredibly reliable power source, providing a steady, predictable trickle of electricity for decades. But whether from solar panels or an RTG, the total power available is always finite, and it is always slowly decreasing over the mission's lifetime as solar panels degrade or the radioactive material decays. This finite power supply means the spacecraft cannot simply do everything at once. Its activities are governed by a strict, rhythmic cycle of charging, conserving, and expending energy. Think of it like managing a household budget with a very limited fixed income. You have to prioritize your spending. You cover your essentials first: the mortgage, the utilities, the groceries. And then, if there's money left over, you can spend on entertainment or a nice dinner out. For a probe, the essentials are its core systems: the computer, the attitude control thrusters, the heaters that keep the electronics from freezing solid, and the receiver that listens for commands from Earth. These systems draw a constant, baseline level of power, the spacecraft's version of a resting metabolism. Everything else is a luxury that must be scheduled and budgeted for. High-power activities are the equivalents of a sprint for an athlete. They demand a huge surge of energy and cannot be sustained for long periods. The single most power-hungry task a probe performs is transmitting data back to Earth. Its radio transmitter requires a significant burst of electricity to shout its findings across billions of miles. Operating certain scientific instruments, like high-power radar or plasma analyzers, also consumes substantial energy. Therefore, the probe's daily life is a carefully choreographed sequence. Its computer follows a detailed power timeline, much like a factory manager following a production schedule. During off-peak times, when power generation is low or when no high-priority tasks are scheduled, the spacecraft enters a low-power sleep or quiet mode. In this state, it is essentially hibernating. Non-essential systems are powered down completely. The main computer might be running only its most basic executive loop. The scientific instruments are in a stand-by mode, drawing minimal current, and the probe conserves every possible watt. Then, as a scheduled high-power activity approaches, the rhythm shifts. The spacecraft might command its heaters to warm up key components in preparation for the coming workload. When the precise moment arrives, it powers up the necessary systems. If it's time to transmit, the transmitter ramps up, drawing a large amount of power from the bus for the duration of the communication pass. If it's time for a complex scientific observation, multiple instruments might be powered on in a specific sequence to avoid overloading the system. This is the peak of the power cycle, the moment of maximum expenditure. Once the task is complete, the probe systematically powers down the high-drain systems, returning to its quiet, conservative state to recharge its batteries both literally and figuratively for the next cycle. This rhythmic dance is not just about daily operations. It's a strategic philosophy that governs the entire multi-decade mission. Mission planners must make difficult choices, balancing the desire for immediate scientific return against the need to ensure the spacecraft is still healthy and powered 10 or 20 years from now. A decision to use extra power for an extended observation campaign today might mean having to reduce the frequency of communications or shorten the operational life of a key instrument later in the mission. For solar-powered missions, this rhythm is even more pronounced and is tied directly to their orbit. A probe orbiting Mars will experience a regular cycle of day and night, with abundant power when in sunlight and a need to rely on batteries during the Martian night. Furthermore, as Mars orbits the Sun, its distance changes, causing the amount of available solar power to vary throughout the Martian year. The probe's power management software must account for all these cycles, constantly recalculating the available energy and adjusting the activity schedule accordingly. This careful, rhythmic allocation of every joule of energy is what transforms a short-term machine into a long-term explorer. It is the discipline that allows a spacecraft like Voyager, with its ever-weakening RTG, to continue operating for over 45 years, its power output slowly declining but its systems gracefully adapting, shedding less critical functions one by one to keep its heart and brain alive, continuing to phone home from interstellar space. This is the silent, vital rhythm of survival, the constant, conscious pulse of energy management that allows a tiny human-made object to endure for generations in the most unforgiving environment imaginable. While we often picture space as a uniformly cold, dark void, the reality for a spacecraft is a brutal and relentless cycle of temperature extremes. On one side of its orbit, the probe is bathed in the unfiltered, searing glare of the sun, with temperatures that can soar high enough to boil water and melt solder. Then, just hours later, as it swings into the shadow of a planet or simply turns its broad side away from the sun, it is plunged into a deep freeze so intense that metal becomes brittle and electronics would simply shatter. This isn't a gentle gradient, it's a violent, regular swing between two destructive opposites. The spacecraft's very survival, therefore, depends on its ability to perform a constant, delicate balancing act, maintaining a stable, room-temperature environment for its sensitive computer brains and instrument hearts despite the inferno and the icebox just inches away through its thin metal skin. This gives rise to the seventh essential rhythm, a silent, vital pulse of thermal regulation that acts as the probe's artificial metabolism, its way of fighting back against the thermodynamic chaos of space. To accomplish this, a probe is dressed in a high-tech cloak known as multi-layer insulation, or MLI. This isn't like the fluffy fiberglass in your attic. It's a complex sandwich of thin, reflective plastic sheets, often coated with a shiny metal like aluminum or gold. Each layer is separated by a delicate mesh, creating a series of tiny, insulating vacuum gaps. This intricate assembly works like a super-efficient thermos, dramatically slowing the transfer of heat from the hot side to the cold side. It reflects the intense solar radiation away, preventing the interior from roasting, and it traps the precious internal warmth inside when the spacecraft is in shadow. But MLI is just passive defense. It can only slow the inevitable. For active control, the probe employs a suite of ingenious devices. One of the most elegant are thermal louvers. These function like the automatic blinds on a smart greenhouse. They are sets of vanes, usually mounted over radiator panels on the spacecraft's exterior. When the internal components start to get too warm, the louvers open, exposing the radiator to the cold blackness of space and allowing excess heat to radiate away as infrared light. When temperatures begin to drop, the louvers snap shut, sealing in the warmth and acting like an insulating blanket. This opening and closing is a continuous, silent ballet, a direct response to the subtle cues from the spacecraft's network of temperature sensors. For more targeted control, the spacecraft relies on electrical heaters, which act like a distributed network of electric blankets. These are not crude, always-on heating elements. They are sophisticated, switched circuits tied directly to the thermal control system. A temperature sensor on a crucial fuel line might detect that it's approaching its freezing point. In response, the computer will automatically switch on a small, localized heater wrapped around that specific component, providing just enough warmth to keep the hydrazine fuel from turning into a solid block of ice. Before a high-power activity, like turning on a camera or a radar instrument, the computer will often command the heaters to pre-warm those components, bringing them up to their optimal operating temperature so they don't suffer thermal shock or produce unreliable data when suddenly powered on. This is the warming up part of the daily cycle, akin to an athlete stretching before a race. Conversely, during long, dormant cruise phases, the heaters might be cycled on a much lower duty cycle, allowing non-critical systems to cool down significantly to conserve every precious watt of power for the essential survival heaters. This careful management of thermal energy is as crucial as managing electrical power. This entire system creates a daily, or even an orbital, rhythm of heating and cooling that is fundamental to the probe's health. For a spacecraft in orbit around Mars, this cycle is incredibly pronounced. During the 40-minute Martian day, the sun-facing side bakes, and the louvers are working constantly to reject the solar heat and the internal waste heat from the electronics. Then, during the 40-minute night, the environment plummets to 100 degrees below zero. The louvers slam shut, and the heaters kick in to maintain a survivable bubble of warmth around the core systems. This is a relentless, unending pulse. It's a rhythm so deeply integrated into the spacecraft's existence that it feels almost biological, like the subconscious regulation of a body's core temperature. A failure in this system isn't just an inconvenience, it's a swift and certain death sentence. If the heaters fail during a shadow pass, critical components will freeze and crack, ending the mission in an instant. If the louvers stick shut while in direct sunlight, the interior will slowly cook, destroying delicate circuitry. This silent, automated pulse of thermal regulation is therefore one of the most fundamental signs of life for a deep space probe, a constant, vigilant effort to carve out a tiny, habitable pocket of Earth-like stability in the most inhospitable environment humanity has ever dared to explore. Now let's step inside the mind of the machine itself. All the rhythms we've discussed, the steady tick of the clock, the celestial cues from the stars, the flow of power and heat, are meaningless without a central intelligence to interpret them and make decisions. This intelligence is the flight software, the probe's persistent consciousness. It doesn't think in a free-form, human way. It operates on a meticulously engineered series of timed loops, creating a cognitive rhythm that is the very essence of its robotic autonomy. Imagine a vast, intricate clockwork where different gears spin at different speeds, all meshing together to drive a single, complex machine. The largest, most fundamental gear is the main executive loop. This is the core operating system, the continuous background process that never, ever stops. It's the probe's basic life function, running on a cycle that might repeat every second or even several times a second. With each iteration, this loop performs a systematic health check. It's like a pilot running through a pre-flight checklist, but one that never ends. It asks a relentless series of questions. Is power nominal? Are temperatures within acceptable bounds? Is the computer memory healthy? Is there any alarm flag raised by any subsystem? It also consults the master mission timeline, a gigantic, pre-loaded schedule of tasks, and executes any commands that are due to run at that precise moment. This executive loop is the probe's foundational awareness, its constant, low-level hum of self-monitoring. But while the executive loop manages the big picture, countless smaller, faster-spinning gears handle the real-time, high-speed demands of staying alive and on course. These are the specialized software loops dedicated to specific, critical functions. The most dynamic of these is often the attitude control loop. This loop runs not once per second, but hundreds of times per second. Its sole purpose is to manage the spacecraft's orientation in space. It continuously reads the high-frequency data from the gyroscopes, feeling for the tiniest uncommanded twist or wobble. It then compares this actual orientation to the desired orientation commanded by the star trackers or the flight plan. If it detects even a minuscule deviation, a drift of a fraction of a degree, it doesn't wait for the main executive loop. It immediately calculates the corrective torque needed and commands the appropriate reaction wheel to spin up or a tiny thruster to fire for a few milliseconds. This all happens in a blink of an eye, a constant, high-speed feedback loop that keeps the spacecraft perfectly poised and stable, its antenna locked on Earth and its instruments pointed at their targets without a hint of vibration or jitter. Another set of fast loops might be dedicated to data processing, taking the raw, noisy stream from a scientific instrument and immediately applying filters and compression algorithms, turning a flood of information into a manageable stream of clean, useful data ready for storage. This layered architecture of loops creates a true cognitive rhythm, a continuous cycle of perception, decision, and action. Perception comes from the sensors, the gyros, the star trackers, the thermometers, the power monitors. Decision happens in the software, where algorithms like the Kalman filter fuse this data into a coherent state of awareness and then choose the appropriate response based on pre-programmed logic. Action is the output, a command to a thruster, an adjustment to a heater, a signal to begin data transmission. This cycle repeats itself thousands of times per second, a relentless, automated drumbeat of existence. It is this rhythm that embodies the probe's autonomy. There is no hesitation, no distraction, no fatigue. While a human operator might miss a subtle anomaly after a long shift, the software loop is eternally vigilant, its attention never wavering. It allows the spacecraft to carry out a mission script of breathtaking complexity over decades, executing sequences with a precision and reliability that is simply beyond human capability. This is the digital heartbeat of the spacecraft, a pulse of ones and zeros that gives a collection of circuits and metal a purpose and a will, enabling it to navigate the void not as a passive piece of debris, but as a thinking, reacting, and truly intelligent explorer. But of course, all of these intricate rhythms of time, orientation, and survival serve a single, magnificent purpose: the acquisition of knowledge. This brings us to the very reason these robotic explorers exist: the cadence of their primary function, the rhythm of data collection and storage. This is not a random or continuous process. It is a carefully orchestrated symphony of observation, a deliberate pulse of gathering and preserving scientific treasure that represents the mission's ultimate heartbeat. Imagine a wildlife photographer on a once-in-a-lifetime safari. They don't simply hold down the shutter button and fire off thousands of photos indiscriminately. They wait patiently, they watch the light, they anticipate the animal's behavior, and then, in a burst of intense, focused activity, they capture the perfect shot. A deep space probe operates on a vastly more complex version of this same principle. Its entire existence is structured around these moments of peak scientific opportunity, and its behavior shifts dramatically between a quiet, patient cruise and a frenetic, data-grabbing encounter. This cadence begins with meticulous planning, long before the spacecraft ever reaches its destination. Mission scientists pore over orbital maps and gravitational models to create an intricate observation campaign. They ask critical questions: when will we be closest to that intriguing volcanic plume on Io? What is the perfect trajectory to map the previously unseen side of a distant moon? During which orbital pass will the Sun be at the ideal angle to illuminate the particles in Saturn's rings? The answers to these questions are translated into a detailed command sequence, a minute-by-minute script that tells the probe precisely what to do and when to do it. This script dictates the rhythm of the instruments themselves. They are not all powered on at once. That would overwhelm the power and thermal systems. Instead, they are activated in a specific, staggered sequence. A plasma wave instrument might be powered up first to establish a baseline reading of the magnetic environment. Then, a few hours later, a high-resolution camera is warmed up and brought online. As the probe reaches its point of closest approach, the most power-hungry and data-intensive instruments, like a synthetic aperture radar or a mass spectrometer, are switched on for their critical, close-range observations. This careful phasing is like an orchestra tuning up, with each instrument joining the ensemble at just the right moment so that when the crescendo arrives, the entire scientific payload is ready to perform in perfect harmony. The peak of this rhythm is truly a sight to behold, if only we could witness it. During a close flyby of a world like Jupiter's moon Europa, the spacecraft enters a state of controlled scientific frenzy. Its computer is executing commands at a blistering pace. Cameras are snapping hundreds of high-resolution images, capturing details of the cracked, icy surface. Spectrometers are analyzing the faint light reflected from the surface, searching for the chemical fingerprints of organic compounds. A magnetometer is measuring subtle fluctuations in Jupiter's magnetic field, looking for the telltale signs of a hidden, global ocean sloshing beneath the ice. Lasers are firing to measure the exact height of surface features. For a few precious hours, the probe is a voracious consumer of data, drinking in every possible photon, every magnetic ripple, every particle it can capture. This data is a torrent, a raw, unrefined flood of ones and zeros that represents a direct glimpse into an alien world. But this is just the first step. The probe's brain cannot simply let this deluge overwhelm its systems. It must immediately begin the crucial work of processing and compression. Just like you might compress a large photo on your computer to send it in an email, the spacecraft software applies sophisticated algorithms to the raw data. It removes redundant information. It might convert a raw image into a more efficient file format, and it prioritizes the most critical data sets. This processing is a rhythm in itself, a cycle of intake, analysis, and condensation, transforming a raging river of information into a manageable, organized stream ready for storage. And storage is the next critical link in this chain. The probe carries its own digital library, a solid-state memory bank with a capacity that, while vast, is still finite. Think of it as a photographer's memory card, but one that cannot be swapped out. Every megabyte is precious. The processed data is carefully written to this memory, with the most unique and high-priority observations given the safest, most protected sectors. The computer maintains a detailed manifest of what is stored where, much like a librarian keeping a meticulous catalog. This sets the stage for the next phase of the rhythm, the long, patient relay. The intense, frantic data collection phase is often brief, but transmitting that data back to Earth is a marathon, not a sprint. After the flyby is complete and the probe is once again cruising at a safe distance, it settles into a slower, methodical routine. It will power up its high-gain antenna, and during its scheduled communication windows with the deep space network, begin the painstaking process of playing back its stored discoveries. It might take days or even weeks to slowly and carefully transmit every last byte of that encounter data across hundreds of millions of miles. This is the mission's exhalation after the sharp intake of breath, the deliberate and careful sharing of its hard-won knowledge. This pulse, the frantic gathering, the careful processing, and the patient transmission, is the definitive rhythm of discovery. It is the process that transforms a silent, flying machine into a genuine extension of human curiosity, a remote sensory organ for our species, methodically building our understanding of the cosmos one carefully orchestrated byte at a time. Even with all these layers of redundancy and self-correction, the harsh reality of space exploration is that components can and do fail without warning. A single cosmic ray, a tiny particle of dust from the early solar system, or the simple, slow wear and tear on a microscopic wire can trigger a cascade of problems that would doom a less prepared machine. This is where we encounter one of the most crucial and resilient rhythms of all, a silent, constant vigil that acts as the spacecraft's robotic immune system. This is the fault protection system, and its core mechanism is a digital heartbeat, a relentless, rhythmic pulse of self-diagnosis that ensures the probe can face the unexpected and live to tell the tale. Imagine a patient in a hospital intensive care unit, connected to monitors that track every vital sign. The steady beep of the heart monitor is the ultimate reassurance that the patient is stable. If that beep stops, alarms sound, and a team of medical professionals springs into action. For a probe billions of miles away, there is no medical team. The spacecraft must be its own doctor, its own nurse, and its own emergency responder. The fault protection system is that internal medical team, and its heartbeat is the fundamental signal that everything is functioning as it should. This system is built around a concept known as a watchdog timer. It's a brilliantly simple yet profoundly effective piece of logic. Critical subsystems throughout the spacecraft, the main computer, the power distribution unit, the attitude control system, are all programmed to regularly send a specific "I'm alive" signal to a central fault protection monitor. This isn't a complex data packet. It's a simple, rhythmic check-in, a digital handshake that says, "All is well in my part of the ship." This pulse might be sent every few seconds, creating a constant, reassuring rhythm of confirmed health. The watchdog timer is always listening for this pulse. As long as the heartbeat arrives on schedule, the monitor remains silent and the mission continues uninterrupted. But if the expected signal from a critical system is even a few milliseconds late or fails to arrive entirely, the watchdog timer immediately recognizes the silence as a symptom of a serious problem. It doesn't wait for confirmation. It doesn't try to diagnose the exact nature of the fault. At the speed of light, it assumes a failure has occurred and initiates a pre-programmed, carefully choreographed emergency response. This is the key to its effectiveness. It trades the uncertainty of a detailed diagnosis for the life-saving speed of a pre-planned reaction. The responses are meticulously designed during years of mission, planning to be the safest possible action the spacecraft can take. The most common and fundamental response is to command the spacecraft into a pre-defined, safe mode. Think of this as the probe curling into a defensive ball. The primary objective is survival. The spacecraft will immediately terminate any non-essential science activities to conserve power. It will then maneuver itself, using its most reliable and simple thrusters, to point its main solar panels directly at the Sun, ensuring a maximum and stable power supply. Simultaneously, it will point its high-gain antenna directly at Earth, re-establishing a clear and simple communication link. It will also switch from its complex, high-performance main computer to a simpler, more robust backup computer, isolating the potentially faulty component. By entering this safe, stable, and predictable state, the probe gives its human controllers back on Earth the one thing they need most: time. Instead of having just minutes to react to a spiraling crisis, the ground team now has hours or even days to analyze the incoming engineering data, diagnose the root cause of the fault, and carefully craft a recovery plan. This rhythm of constant self-checking and automated response has saved countless missions. The Mars rover's Spirit and Opportunity, for instance, entered safe mode dozens of times during their long careers, surviving dust storms, computer glitches, and memory errors, always because this watchdog heartbeat detected an anomaly and triggered the survival protocol before the situation became irreversible. This system extends far beyond a single central monitor. It's a layered defense, a network of watchdogs guarding different aspects of the spacecraft's health. There might be a separate monitor solely for attitude control, watching for any tumble or spin that exceeds safe limits. Another might guard the power bus, ready to trip a circuit breaker if it detects a dangerous power surge or a short circuit. Yet another might monitor temperatures, ready to power down an overheating instrument before it cooks itself. Each of these specialized watchdogs operates on its own rhythmic cycle, creating a symphony of self-preservation. This layered approach means that a failure in one system doesn't necessarily bring down the entire spacecraft. The fault can be contained and isolated, much like the watertight compartments in a ship's hull. The rhythm of the fault protection heartbeat is therefore the rhythm of ultimate resilience. It is the embodiment of a design philosophy that accepts the inevitability of failure and builds a system not to avoid it entirely, but to withstand it, to adapt to it, and to recover from it autonomously. It is this relentless, silent pulse of "I'm alive" that allows a fragile vessel of human ingenuity to endure for decades in an environment where a single missed beat could mean eternal silence. Now, let's peer into the mathematical engine room of the probe's navigation system, where raw data is transformed into reliable knowledge. This brings us to a truly elegant algorithm known as the Kalman filter, a process that creates a rhythm of refined estimation, a kind of artificial intuition for the spacecraft. At its heart, the Kalman filter solves a fundamental problem. Every single sensor reading, no matter how advanced, contains a tiny amount of noise, a little bit of statistical fuzziness. A star tracker might be off by a few arc-seconds, a gyroscope might have a minuscule drift, and even the pristine signal from Earth used for radio navigation has infinitesimal timing jitter. If the probe acted on every single one of these imperfect measurements as if it were absolute gospel, its behavior would be jittery and unstable, constantly overcorrecting for errors that aren't really there. It would be like trying to drive a car by staring only at the vibrating needle of the speedometer, jerking the accelerator on and off with every tiny fluctuation. What the probe needs is a smooth, weighted average, a best guess that incorporates both what its sensors are telling it right now and what it confidently knew a moment ago. The Kalman filter is the genius that performs this continuous blending. The algorithm operates on a beautifully simple two-step rhythm that repeats hundreds of times per second: predict and update. First, in the prediction step, the filter takes the probe's last known best estimate of its state, its position, its velocity, its orientation, and uses its knowledge of the spacecraft's dynamics to project that state forward in time. It essentially says, based on where we were a millisecond ago, and given that our thrusters are off and we're simply coasting, here is where we should be right now. This prediction isn't a wild guess. It's a sophisticated forecast based on the laws of physics. But this prediction is also imperfect because we can't perfectly model every single tiny force acting on the spacecraft. So the filter assigns a certain level of uncertainty to its own prediction. Then comes the update step. A new, real sensor measurement arrives, fresh from a star tracker or a gyroscope. This measurement is also imperfect with its own known level of uncertainty or noise. The Kalman filter doesn't just throw away its prediction and accept the new measurement. Instead, it performs a brilliant mathematical dance. It compares its prediction to the new measurement, and then it calculates a new, refined estimate that lies somewhere between the two. The key is how it weights this average. If the sensor is known to be very reliable and precise, the filter will trust the new measurement more, pulling the final estimate closer to that reading. If the sensor is noisy or the prediction is considered very confident, the filter will trust its own forecast more. You can experience a crude version of this process yourself. Imagine you're trying to guess the weight of a strange fruit at a market. You pick it up, that's your first noisy sensor measurement. It feels like it might be about 300 grams, but your hand isn't a perfect scale. Then you make a prediction based on your knowledge of similar fruits. You predict it should weigh 250 grams. Your brain, acting as a Kalman filter, naturally blends these two pieces of information. You don't stubbornly cling to your initial feeling, nor do you completely ignore it in favor of your prediction. You intuitively settle on a refined estimate, perhaps 270 grams, that feels more right than either number alone. The probe's filter does this with relentless mathematical precision for dozens of state variables simultaneously. This continuous cycle of predict and update creates an incredibly stable and accurate picture of reality from a stream of jittery, imperfect data. It smooths out the bumps and glitches, allowing the spacecraft to see its own trajectory with a clarity that no single sensor could ever provide. This rhythmic refinement of knowledge, this constant honing of intuition, is the silent cognitive engine that enables a machine to navigate with such breathtaking precision across the mind-boggling emptiness between worlds. But even with the constant, gentle nudges of trajectory correction maneuvers, Some missions demand a level of precision so absolute that it borders on the impossible. This brings us to one of the most breathtaking rhythms in the entire symphony of spaceflight, a moment where all the subtle pulses of time, orientation, and calculation must converge with perfect harmony, the gravitational keyhole transit. Imagine you are an archer, but instead of aiming for a large target 100 yards away, you are standing on one side of a continent and must fire an arrow through a keyhole in a door on the opposite coast. Now imagine that both you and the door are moving at tens of thousands of miles per hour on independent, curved paths through space. This is the scale of the challenge navigators face when they target a gravitational keyhole. A keyhole is not a physical object. It is a point in space, a precise location defined by the complex interplay of gravitational forces. It is a gateway, a specific point in a planet's or moon's gravitational field that, if a spacecraft passes through it, will guarantee a future desired outcome. For a mission like Cassini, a keyhole might have been a point near Saturn that would ensure the spacecraft would be pulled into a specific orbital path, allowing it to repeatedly fly by the moon Titan. For the Mars rovers, the keyhole was an entry point into the Martian atmosphere, a location and angle so precise that it would enable the spacecraft to survive the fiery descent and land within a tightly constrained ellipse on the surface. Missing this keyhole by even a few hundred meters, a minuscule error at an interplanetary scale, could mean the probe would skip off the atmosphere and back into space, or plunge in at too steep an angle and burn up. The entire multi-year, billion-dollar journey hinges on hitting this microscopic target. The approach to a keyhole is where the mission's rhythm shifts from a steady cruise to a tense, accelerating crescendo. In the final days and hours, the spacecraft enters a phase of hyper-precise navigation. The normal, periodic trajectory correction maneuvers are no longer sufficient. The team on Earth and the probe's autonomous systems begin a process of continuous refinement, using every available sensor and every trick of radio navigation to pinpoint the spacecraft's location with an accuracy that can be measured in mere meters. The Doppler shift of the radio signal is analyzed to an almost absurd degree, revealing velocities down to fractions of a millimeter per second. The ranging data, the time it takes for a signal to make the round trip, is scrutinized to determine distance with the precision of a master watchmaker. On board, the star trackers and gyroscopes are working in overdrive, their fused data providing an unwavering sense of attitude, because the direction of the final, critical engine burn is as important as its duration. This is the moment where the Kalman filter, that rhythm of refined estimation, truly proves its worth, smoothing out the last remnants of sensor noise to present the computer with a crystal-clear picture of reality. The final trajectory correction maneuver, often executed just 24 hours or even mere hours before the keyhole transit, is not a gentle nudge. It is a surgical strike, a calculated pulse of thrust so precise that it is often measured in centimeters per second. It is the last fine-tuning turn of the dial, the final adjustment of the crosshairs after years of travel. Then comes the transit itself, a fleeting, silent, and almost anticlimactic event. There is no dramatic flash of light, no roaring sound. The spacecraft simply coasts, a silent speck of metal, through an imaginary point in the void. For the probe, it might be just another millisecond in its long journey, logged in its data stream as a minor navigational milestone. But for the engineers and scientists watching from a billion miles away, it is the culmination of a decade of work. It is the moment of truth. All the hidden rhythms have led to this instant. The unwavering pulse of the atomic clock ensured the burn was timed perfectly. The celestial dance of orbital mechanics defined the keyhole's location. The guiding beacon of the stars kept the spacecraft pointed correctly. The symphony of sensor fusion provided the confidence to make the final move. And the autonomous correction rhythm delivered the final, flawless nudge. When the telemetry confirms the spacecraft has passed through the keyhole, a wave of relief and triumph washes over mission control. The probe is now locked onto its final path, its future guaranteed by the immutable laws of gravity. It is a testament to human ingenuity, a demonstration that we can not only understand the cosmos but also use its own forces as a tool, threading a needle with a machine across an ocean of space and time. This perfect keyhole transit is the ultimate expression of control in a seemingly chaotic universe, a silent, rhythmic dance step executed with a perfection that still inspires awe. Now let's bring this entire concept down to the surface of another world, where the rhythm of communication transforms into a beautifully complex relay dance. On Mars, a rover like Perseverance faces a unique challenge. Its direct link to Earth is incredibly weak, like trying to whisper across a crowded, noisy stadium. The rover's small antenna and limited power supply simply aren't suited for shouting its day to hundreds of millions of miles back to our planet. Instead, it relies on a celestial intermediary, a network of robotic companions circling overhead in the Martian sky. This is the rhythm of interplanetary networking, a layered system of data handoffs that operates with the precision of a well-rehearsed ballet. The primary partners in this dance are the rovers on the ground and the orbiters above. Think of the Mars Reconnaissance Orbiter or the European Space Agency's Trace Gas Orbiter as high-flying communication satellites, but for an entire planet. These orbiters are equipped with powerful, large dish antennas and substantial solar panels, giving them the muscle to send strong signals across the vast interplanetary gulf to the giant receiving dishes of Earth's deep space network. Their job is to act as data mules, flying over the rover's location and collecting its precious scientific findings. For the rover, this is a game of patience and perfect timing. It doesn't transmit continuously, that would drain its batteries for little gain. Instead, it stores its accumulated data, high-resolution images, soil analysis results, and weather reports in its onboard memory, patiently waiting for its scheduled talk time. Several times each Martian day or sol, the rover knows to look up at the sky. It listens for the approaching orbiter, and during a brief, precious window when the orbiter is visible above the horizon, it initiates a rapid, high-bandwidth transfer. This uplink is a focused, local conversation, a powerful burst of data traveling a relatively short distance of a few hundred miles straight up. The rover pours out gigabytes of information in a matter of minutes, emptying its memory banks and readying itself for a new cycle of discovery. Then, just as quickly as it began, the connection is broken as the orbiter flies over the horizon, and the rover returns to its silent, solitary work. But the orbiter's job is far from finished. It is now carrying a treasure trove of data from not just one, but potentially several different surface assets. It has its own complex rhythm to manage, a separate schedule of communication windows with Earth. The orbiter cannot simply turn and transmit this data immediately. It must wait for its own moment in the cosmic schedule, when Mars itself is positioned correctly relative to Earth and a giant antenna in California, Spain, or Australia is pointed in its direction. So, the orbiter stores the bundled data from the rover, along with its own scientific observations of the Martian atmosphere and surface. When its scheduled downlink window with Earth opens, it powers up its powerful transmitter and begins the long-distance call home. This transmission is a slow, methodical process as it pushes a massive amount of data across the immense distance, a task that can take hours. This creates a fascinating, staggered rhythm across the solar system. A photograph taken by the Perseverance rover on a Monday might be received by the Orbiter on Tuesday, but it isn't actually seen by scientists at the Jet Propulsion Laboratory until Wednesday, after the orbiter has had its chance to relay the entire data package. This relay system is a masterpiece of efficiency. By using the orbiters as intermediaries, the rovers can use small, low-power antennas, saving their energy for driving and conducting science. The orbiters, with their powerful transmitters and abundant solar power, act as a centralized, high-speed internet hub for the entire Martian system. This layered approach multiplies the scientific return of every mission, creating a synchronized network where robots work in concert, their individual rhythms of collection, storage, and transmission interlocking perfectly to form a continuous stream of knowledge flowing from the red plains of Mars all the way back to our own blue world. This brings us to a phenomenon so subtle and counterintuitive that it challenges our most basic understanding of reality, a rhythm dictated not by engineering but by the fundamental fabric of the cosmos itself, the challenge of time dilation. At the heart of Einstein's theory of relativity lies a startling truth that feels more like science fiction than established physics. Time is not a universal constant ticking away at the same rate for everyone, everywhere. Instead, it is a malleable, personal experience, a river that flows at different speeds depending on where you are and how fast you are moving. For a deep space probe, this isn't an abstract philosophical concept. It's a practical navigational problem that must be solved with mathematical precision. The theory tells us that two powerful effects warp the passage of time. The first is velocity. The faster an object moves through space, the slower time passes for it relative to a stationary observer. This is known as special relativity. The second is gravity, described by general relativity. The stronger the gravitational field an object is in, the more time slows down. A probe on a high-speed trajectory through the solar system is subject to both of these effects, creating a unique and personal time frame that diverges from our own here on Earth. Consider the practical implications of this. Imagine a pair of perfectly synchronized atomic clocks, both counting out nanoseconds with flawless, identical precision. Now place one clock here on Earth and launch the other onboard a spacecraft like Voyager, speeding away from us at tens of thousands of miles per hour. According to Einstein's equations, the clock on the fast-moving spacecraft will gradually begin to lag behind the one on Earth. It's not that the clock is malfunctioning. Time itself is literally passing more slowly for the traveling clock. From our perspective on Earth, the probe is living in a slightly slowed-down version of reality. Its internal atomic clock, the very metronome of its existence, is ticking just a tiny bit slower. The cycles of its central computer are processing instructions at a marginally reduced rate. Even the chemical reactions in its circuits and the decay of its plutonium power source are happening in this altered time frame. The difference is incredibly small. For a mission like Voyager, it might only amount to a few seconds over several decades. But in the world of interplanetary navigation, where we are calculating positions down to meters and velocities to fractions of a millimeter per second, those accumulated seconds represent a significant error. An uncorrected time discrepancy of just 1 second could throw off the calculation of a probe's position by the distance light travels in that second, a staggering 300,000 kilometers. Over the course of a long mission, this relativistic drift could mean the difference between a spectacular success and missing a planetary encounter by a wide margin. Therefore, the probe's navigational software cannot treat time as a simple, absolute quantity. It must be a relativistic cartographer, constantly applying corrections to bridge the gap between its own personal flow of time and the terrestrial time used by its human controllers. This is not a one-time adjustment made at launch. It is a continuous, dynamic calculation woven into the very fabric of the navigation algorithms. The software must account for the probe's constantly changing velocity as it speeds up during planetary flybys and slows down as it climbs away from the Sun. It must also factor in the varying gravitational fields it passes through. Time slows a little more when the probe swings close to a massive planet like Jupiter, and a little less when it's cruising through the relatively weak gravitational field of the outer solar system. The software essentially runs a double ledger. It tracks mission elapsed time according to its own onboard clock, and it simultaneously computes what the corresponding time would be back on Earth, a value known as coordinated universal time. Every single navigational measurement, every timestamp on a piece of scientific data, and every scheduled engine burn is translated between these two frames of reference. This ensures that when the probe calculates its position by timing the round trip of a radio signal from Earth, it is using a timescale that is perfectly synchronized with the giant antennas of the deep space network, despite the fact that the two are experiencing time at fundamentally different rates. This relativistic rhythm is perhaps the most profound and hidden of all because it is not something we engineered into the spacecraft. It is a law of nature that we discovered and to which we must humbly adapt. It is a silent, invisible force that acts upon every atom of the probe, a gentle tug on the fabric of its existence imposed by the structure of the universe. When we successfully correct for it, we are doing more than just solving a complex math problem. We are demonstrating a deep and functional understanding of the cosmos. We are acknowledging that the reality we experience in our daily lives on Earth is just one perspective, and that to explore the greater universe, we must learn to see through the lens of relativity. The probe, in its silent journey, becomes a practical testbed for Einstein's theories, its flawless navigation a continuous, ongoing verification of a concept that once existed only on chalkboards and in thought experiments. This synchronization across diverging timelines is a triumph of human intellect, a silent partnership between a machine built on classical principles and a universe that operates by relativistic rules. It is the ultimate proof that to explore the cosmos, we must not only build better machines, but also learn to think in entirely new ways about the very nature of space and time. After years of traveling through the void, a deep space probe bound for the outer planets enters a state that seems almost paradoxical, a period of profound quiet. This is the dormant cruise phase, a long, rhythmic interlude of hibernation that stands in stark contrast to the brief, explosive moments of discovery that define its mission. Picture a bear sleeping through the winter, its metabolism slowed to a bare minimum to conserve energy for the coming spring. In the same way, a spacecraft like Cassini, on its way to Saturn, or New Horizons racing toward Pluto, becomes a silent, sleeping traveler for the vast majority of its journey. During this extended cruise, the probe's existence is pared down to the absolute essentials. Its powerful main computer switches to a low-power mode, running only the most fundamental executive loops. The intricate scientific instruments, the high-resolution cameras, the sensitive spectrometers, the complex plasma analyzers, are powered off completely, their electronic eyes closed. The spacecraft's main transmitter, its powerful voice, falls silent. Only the barest skeleton crew of systems remains on duty. The fault protection watchdog maintains its lonely vigil, listening for the rhythmic heartbeat of core systems. The essential heaters cycle on and off to keep the vital organs from freezing. The attitude control system makes tiny, infrequent adjustments to keep the spacecraft stable and its solar panels, if it has them, angled toward distant, fading sun. This isn't a state of inactivity born of laziness. It is a deliberate, strategic rhythm of conservation. The probe is marshalling its resources, saving every joule of power from its RTG and preserving the finite lifespan of its moving parts for the single most important period of its life, the encounter. This long, slow heartbeat of the cruise phase can last for years, a 7-year journey to Jupiter, a nearly decade-long voyage to Pluto. For the engineers and scientists on Earth, this period is one of patient, long-term monitoring. They receive weekly or even monthly engineering beacons, simple status reports that essentially say, "All is well, I am alive and on course." The intense daily hustle of mission control gives way to a quieter, more methodical rhythm of checking trajectory data and planning for the distant future. The spacecraft itself becomes a background presence, a silent promise of future wonders, traveling on a path calculated years before. But this deep sleep is not a coma. The probe is always listening, its electronic ear cocked for a potential wake-up call from Earth. Mission controllers can send a command to rouse it from its slumber for a scheduled trajectory correction maneuver or to test a backup system, after which it will peacefully return to its dormant state. This ability to sleep and wake on command is a critical part of its long-term resilience, allowing it to endure the epic durations of interplanetary travel without wearing itself out. Then, after years of silence, a scheduled alarm clock rings deep within the probe's memory. The moment of encounter is approaching. This triggers one of the most dramatic rhythmic transitions in all of space exploration, the shift from dormant cruise to active encounter. It begins not with a sudden jolt, but with a gradual, systematic reawakening. Weeks or even months before the main event, the spacecraft's computer begins executing a long, pre-loaded sequence of commands. It's like a conductor quietly tapping the stand before a symphony, signaling the musicians to ready their instruments. One by one, systems are brought back online. Heaters are commanded to warm the frozen joints and electronics of the science payload. Each instrument is powered up in a specific sequence, put through a series of diagnostic tests to ensure it survived the long cruise in good health. The star trackers and gyroscopes are calibrated with fresh data. The main computer transitions to its high-performance mode, its cognitive loops speeding up in preparation for the torrent of data and decisions to come. This wake-up call is a carefully orchestrated process, a slow crescendo that builds anticipation not just for the machine, but for the entire team on Earth. The quiet engineering reports are replaced by a flood of telemetry as the probe confirms that every system is a go. When the encounter phase finally begins, the rhythm of the mission transforms completely. The slow, steady heartbeat of the cruise explodes into a rapid, excited, almost frantic pulse of activity. The probe is no longer a sleeper. It is a fully alert, hyper-aware scientific observatory. Its days are no longer measured in quiet solitudes, but in a meticulously planned timeline of observations, each one more critical than the last. For a fly-by mission like New Horizons at Pluto, this phase might last for just a few weeks, with a core period of intense activity mere days around the closest approach. For an orbiter like Cassini at Saturn, the encounter phase was its entire operational life at the planet. A 7-year-long ballet of orbital adjustments and targeted flybys of Titan and Enceladus. During this time, the spacecraft is constantly busy. Its computers are processing thousands of commands per day. Its instruments are cycling on and off, capturing images, measuring magnetic fields, and sampling dust particles. Its thrusters are firing frequently for fine-tuning its trajectory. The data storage banks fill at an astonishing rate, and the communication system works overtime between observation periods to dump this precious cargo back to Earth. This is the probe's moment in the spotlight, the entire reason for its multi-year journey. The strategic rhythm of the long dormancy pays off here in spades. By conserving its energy and preserving its systems during the cruise, the spacecraft arrives at its target with the power, health, and capability to perform at its absolute peak. It can execute complex sequences without hesitation, capture once-in-a-lifetime scientific data, and adapt to surprises, all because it spent years in a peaceful, energy-saving slumber, dreaming of the moment it would finally awake to explore a new world. But as we push the boundaries of what a single, sophisticated probe can accomplish, a far more ambitious and transformative vision is beginning to take shape, one that moves beyond the lone explorer to something resembling a coordinated flock of robotic birds. Picture this: instead of one large, costly, and complex spacecraft orbiting Jupiter, imagine a cloud of dozens or even hundreds of smaller, simpler probes all working in concert. Each one might be no larger than a briefcase, but together they would form a single, distributed sensor swarm, a vast, intelligent net cast around the entire planet. This concept of swarm exploration introduces a breathtaking new layer of complexity to our symphony of rhythms, moving from the carefully composed score of a soloist to the dynamic, improvisational jazz of an entire orchestra. The fundamental rhythm here is no longer just about a single probe maintaining its internal state. It becomes swarm synchronization, a collective pulse that must be negotiated and maintained in real time among all the individual members. This requires a radical shift in how these probes communicate. They cannot all phone home individually to Earth. That would overwhelm the deep space network and introduce impossible delays. Instead, they must talk to each other, creating a resilient, self-healing mesh network in the space around Jupiter. In this network, each probe is both a scientist and a communication node. Data collected by one probe on the far side of the planet might be passed, node by node, through a dozen of its neighbors before finally reaching a designated leader probe with a powerful antenna that bundles all the collective data for the long-distance transmission back to Earth. This creates a whole new set of internal rhythms: the rapid-fire, local rhythm of peer-to-peer data handshakes, and the slower, more deliberate rhythm of aggregated data being passed toward the swarm's communication hub. They would need to share more than just data. They would need to share time. To coordinate a simultaneous measurement of a planet-wide magnetic field, or to triangulate the source of a radio burst from Io, every single probe in the swarm must share a perfectly synchronized sense of time, likely by designating one probe's atomic clock as the master timekeeper for the entire collective, with constant, rhythmic updates being broadcast to keep everyone in lockstep. This shared timing would be the metronome for the entire swarm, the foundational beat that allows their individual actions to coalesce into a single, coherent observation. The true power of this approach emerges from this local coordination. The swarm wouldn't need a micromanaging conductor on Earth telling each probe exactly what to do. Instead, their collective behavior would emerge from simple, pre-programmed rules governing their interactions with their immediate neighbors. This is a principle often seen in nature: a school of fish evading a predator or a flock of birds wheeling through the sky doesn't have a leader calling out every turn. Each individual just follows a few basic rules: stay close to your neighbors, match their speed, and avoid collisions. From these simple, local rhythms of interaction, a complex and beautiful global pattern emerges. A robotic swarm would operate on a similar principle. A probe might have a rule that says, if my neighbor detects a high concentration of methane, adjust my orbit to move closer to it and take a more detailed measurement. Another rule might be, If I am part of a group measuring a storm in the Great Red Spot, space myself evenly from my neighbors to create a perfect sensor grid. The swarm would constantly self-organize based on the scientific phenomena it encounters, its formation dynamically reshaping itself in response to the environment. This emergent intelligence makes the system incredibly robust. If one probe fails, the swarm simply reconfigures its network around the gap, and the mission continues almost unaffected. It's a resilient, adaptive, and immensely powerful way to explore, turning a collection of simple units into a single, sophisticated, and planet-wide scientific instrument. This vision of a future probe represents a profound leap from simply responding to problems to actively anticipating them, moving from a reactive mindset to a truly predictive one. The key to this transformation lies in a more advanced form of artificial intelligence, one that doesn't just execute commands but develops a deep, intuitive sense of its own body and its place in the environment. Today's fault protection systems are undeniably brilliant, but they work like a list of specific symptoms in a medical textbook. They are programmed to recognize a finite set of known failure modes. If the pressure in a fuel line drops below this value, then switch to a backup. If the temperature on this component exceeds that threshold, then power it down. It's a system built on if this, then that logic, and it has saved countless missions. But what about the failures we haven't imagined? What about the subtle, slow-moving degradations that don't trigger any single alarm but, in combination, signal an impending catastrophe? This is the limitation that AI-driven anomaly detection is designed to shatter. The core of this new approach is the establishment of a dynamic, living baseline. Imagine the AI as the spacecraft's personal physician, but one that has monitored its patient every single second of its life. During the initial, healthy phase of the mission, the AI would engage in a period of intense learning. It wouldn't just record data, it would learn the intricate, interconnected rhythms of a perfectly functioning spacecraft. It would learn that when the main transmitter is active, the power bus voltage typically dips by exactly 0.42 volts, and that the temperature on the external communication amplifier always rises by 11 degrees Celsius within the first 3 minutes of operation. It would learn the complex, seasonal dance of the spacecraft's internal temperature as its orbit carries it closer to and further from the Sun. It would map out the unique acoustic signature of every reaction wheel and pump, the subtle vibration patterns that are the music of a healthy machine. This baseline isn't a single number, it's a multi-dimensional tapestry of relationships, a statistical portrait of normal in all its beautiful, complex detail. This becomes the AI's sense of the probe's healthy vital signs, its personal definition of wellness. Once this baseline is ingrained, the AI begins its true work, a rhythm of continuous, microscopic comparison. It's a silent, ceaseless vigil, listening to the hum of the spacecraft systems and comparing the real-time symphony against the remembered score of perfection. This isn't about looking for red lines being crossed, it's about detecting the faintest wrong note in a chorus of millions. For instance, the AI might notice that a particular heater is now drawing 0.01% more current than it did a year ago to achieve the same temperature. On its own, this is meaningless, well within any engineer's margin of error, but the AI doesn't see it in isolation. It correlates this tiny deviation with 1,000 other data points. It might notice that this slight power increase began precisely 96 hours after a tiny, scheduled thruster burn that imparted a minuscule vibration through the frame. The AI's model might then hypothesize that a tiny wire connection to that heater has become slightly less efficient due to that vibration, a microscopic fault that would be completely invisible to any traditional system. This is the power of context. The AI isn't just sensing a symptom, it's diagnosing a cause by understanding the hidden connections between seemingly unrelated systems. This proactive awareness opens the door to preventative action on a scale we can barely imagine today. Instead of waiting for a component to fail and then switching to a backup, the AI could initiate graceful degradation. Let's say its algorithms predict with 95% confidence that a specific memory bank has a high probability of developing a fault within the next 6 months based on increasing error correction rates and slight changes in its power on signature. The AI could autonomously decide to begin a slow, deliberate migration of critical data off that memory bank. It could reconfigure the onboard software to rely less on that resource, gently sidelining it before it ever causes a problem. It could even schedule a gentle diagnostic test, a system checkup, during a quiet mission phase to gather more data and confirm its hypothesis, then uplink a detailed health report to Earth saying, "I've detected an early-stage anomaly in memory bank C. I have taken mitigating steps and project a 90% chance of full functionality for the remainder of the mission if current protocols are maintained." This transforms the mission lifecycle. A spacecraft is no longer a collection of parts with a fixed expiration date. It becomes an evolving entity that can manage its own aging process, identifying weak points and shifting resources to compensate, thereby extending its operational life from years to decades. This is not just maintenance, it's a form of robotic self-preservation, an intelligent pulse of health consciousness that could allow our robotic envoys to operate for centuries, their minds continually learning and adapting to the slow creep of entropy in the harsh environment of deep space. Yet, for all its elegant independence, the probe is never truly alone. Across the vast and silent gulf it travels, an entire team of human beings maintains a constant, rhythmic vigil, their work synchronized not with the ticking of an atomic clock, but with the familiar cadence of a 24-hour day and the slow turn of the Earth. This is the human rhythm of ground team planning, a carefully choreographed dance of analysis and foresight that forms the other half of this extraordinary partnership. While the spacecraft manages the immediate, split-second realities of survival and navigation, the men and women in mission control are its long-term strategic mind, looking weeks, months, and even years into the future to chart a course through the cosmos. This collaboration across billions of miles is not a simple remote control operation. It is a complex, asynchronous dialogue, a continuous cycle of listening, thinking, and speaking that bridges the immense communication delay. The ground team's existence is structured around the precious, fleeting communication windows with their distant robotic partner. The arrival of a new data downlink is an event, a moment of revelation. That stream of telemetry, containing everything from stunning images of an alien world to mundane readings of battery voltage and component temperatures, is the spacecraft's detailed letter home. The first human rhythm is therefore one of intense, focused reception and distribution. As the data pours in from the giant dishes of the deep space network, it is immediately routed to specialized teams. The guidance and navigation team dives into the precise trajectory data, verifying that the probe is exactly where their models predicted it would be. The spacecraft systems team combs through the engineering data, their experienced eyes scanning for any subtle deviation from the norm: a slight pressure drop in a thruster fuel line, a tiny increase in the current drawn by a reaction wheel. The science teams, meanwhile, eagerly unpack the latest observations, their work just beginning as they process images and spectra, looking for the clues that could rewrite our understanding of the solar system. This initial analysis phase is a symphony of specialized expertise. a rapid, methodical assessment conducted in the brief hours between the end of one downlink and the beginning of the next planning cycle. Once the data is understood, the rhythm shifts from analysis to decision-making and command creation. This is where the human role transitions from observer to director. The various teams gather in dedicated rooms or connect through vast teleconferences, their discussions a blend of rigorous engineering and creative problem-solving. They are not deciding which way to turn the spacecraft right now. That would be impossible. Instead, they are building a detailed set of instructions for the next chapter of the mission, a block of commands that might cover the next week, month, or even an entire encounter sequence. This command sequence is a miniature computer program in itself, a time-tagged script that tells the probe what to do and when to do it. Every single action, no matter how small, must be planned, validated, and tested. A command to take a picture of a specific moon must specify the exact exposure time, the filter to be used, and the precise moment to execute, all while ensuring the maneuver to point the camera doesn't conflict with a scheduled communication pass or overtax the power system. The teams must think several steps ahead, anticipating potential problems and building in contingencies. What if a star tracker is momentarily confused by a bright planet? What if the data volume from a particular observation is larger than expected? The command sequence is laced with fault protection logic and conditional branches, allowing the spacecraft to make intelligent, pre-approved choices on its own, guided by the strategic intent of the humans back on Earth. This meticulous, collaborative process of building these command blocks is a rhythm of intense creativity and painstaking review, a human effort to imbue the autonomous machine with a clear and resilient plan for the future. Finally, the cycle culminates in the uplink, the moment when the ground team speaks to its distant explorer. During the next scheduled communication window, the carefully constructed block of commands is transmitted from a giant antenna on Earth, racing at the speed of light toward the probe. This is not a moment of tension, but one of quiet confidence. The team has done its work, the plan is sound. The spacecraft receives this digital package and stores it securely in its memory to be executed according to its own internal timeline. And then the human rhythm begins anew. The team doesn't rest. They immediately start planning for the cycle after next, using the data they just received to refine their models and prepare the subsequent set of commands. This creates a continuous, overlapping loop of activity on Earth, a human heartbeat that pulses in steady, deliberate time with the robotic heartbeat out in the void. The probe operates with the flawless precision of a machine, but its purpose, its direction, and its very reason for being are gifts from the human team that guides it. This partnership is a testament to a different kind of intelligence, not the swift, autonomous intelligence of circuits and code, but the patient, strategic, and deeply creative intelligence of human curiosity, working in perfect concert with its creation to explore further than either could ever go alone. This final rhythm, the end of mission protocol, is perhaps the most bittersweet of all. It's the carefully planned cadence of a graceful exit, a deliberate and purposeful conclusion written into the mission's very first plans. Unlike a failure, which is a sudden, silent end, this is a final, eloquent statement, a last act of scientific discovery and responsibility that ensures the probe's legacy is one of pure contribution right up to its final moment. For a spacecraft that has spent decades as a vital, thinking presence in the void, its end is not an accident but a final, orchestrated maneuver. The most iconic example of this is without a doubt the Cassini mission's grand finale at Saturn. After 13 incredible years orbiting the ringed giant, its fuel was running low. Mission planners faced a critical decision. Let the spacecraft run out of propellant and become an uncontrollable piece of space junk, adrift in the Saturn system, or guide it on a final, purposeful path. The choice was clear, and it was rooted in a profound ethical principle known as planetary protection. Cassini had not been sterilized to the extreme standards required for a lander, as it was never intended to touch a potentially habitable world. But its discoveries had revealed that moons like Enceladus, with its subsurface ocean and geysers of water ice, and Titan, with its lakes of methane, were prime candidates in the search for life. Allowing a contaminated spacecraft to accidentally crash into one of these pristine environments was unthinkable. It would be a tragic violation of our cosmic responsibility, potentially seeding a new world with terrestrial microbes and forever compromising future scientific investigation. So, the team designed an end-of-life rhythm that was both scientifically spectacular and ethically impeccable. This final choreography began with a nudge, a gentle push from its thrusters that sent Cassini on a series of 22 daring, week-long orbits that swooped between the planet and its inner rings, a region no human-made object had ever ventured into before. This was not a quiet coast toward an end. It was a final, feverish sprint for discovery. Each close pass was a unique scientific bonanza. The probe's instruments sampled ring particles and molecules of Saturn's upper atmosphere directly, providing data that could never be gathered from a distance. Its cameras captured the most stunning, close-up images of the rings and the planet's swirling cloud tops. Every orbit was a treasure hunt, and every data downlink was packed with revelations. This phase was the crescendo of the entire mission, a rhythm of intense observation and transmission that pushed the spacecraft and the ground team to their limits. For the scientists and engineers, it was an emotional roller coaster, the thrill of receiving once-in-a-lifetime data, tempered by the knowledge that each orbit brought their robotic partner closer to its inevitable end. The spacecraft itself, oblivious to the sentiment, performed flawlessly, executing its final command sequences with the same precision it had maintained for nearly 20 years in space. The final orbit was the masterstroke of this concluding symphony. On its last pass, Cassini used the gravity of Titan one final time, a parting gift from a moon it had studied so intimately, to bend its trajectory inward, setting it on an irreversible collision course with Saturn itself. As it made its final descent, it continued to do what it was built to do. It gathered data. Even as it plunged into the upper atmosphere, its thrusters fought to keep its high-gain antenna pointed at Earth for as long as possible, streaming back real-time information on the composition and structure of the gas giant's atmosphere. This was a final, desperate shout into the growing storm, a last burst of knowledge sent back across 870 million miles. Then, at a precisely calculated moment, the friction and pressure became too great. The thrusters could no longer maintain stability. The spacecraft began to tumble, and within minutes it was vaporized, becoming a permanent, incandescent part of the planet it had devoted its life to understanding. The signal from Cassini ceased, and in the silent control rooms on Earth, its journey was over. This final, fiery rhythm was not a death, it was a transformation. It was a planned and controlled act that protected the future of exploration while wringing every last drop of science from a mission that had already given so much. It was a respectful and dignified end, ensuring that the story of Cassini would forever remain one of pure discovery, its legacy untainted by the risk of biological contamination. This final, self-sacrificing pulse is the ultimate expression of a mission's purpose, a final, rhythmic beat that echoes long after the spacecraft itself is gone. But to truly appreciate the silent, predictable framework that makes all of this possible, we must descend past the rhythms of the machine and even the rhythms of the cosmos, down to the bedrock of reality itself. This brings us to the deepest and most profound rhythm of all, the one that underpins every single calculation, every navigation solution, and every precisely timed engine burn, the unwavering, immutable presence of the universal physical constants. These are not rhythms in time, but rhythms in the very fabric of existence, the fixed numerical values that define how the universe operates at its most fundamental level. Think of them not as instruments in the orchestra, but as the fundamental laws of acoustics that make sound and music even possible. They are the absolute rules of the game, the inviolate sheet music upon which the entire grand symphony of spaceflight is composed. Without these constants, the cosmos would be a realm of pure chaos, a place where the laws of physics changed from one moment to the next, where gravity might be strong today and weak tomorrow, and where the speed of light was merely a suggestion. In such a capricious universe, the very idea of launching a probe on a multi-year journey to a precise point billions of miles away would be laughable. It would be like trying to compose a symphony in a hall where the speed of sound changed randomly every few seconds. The probe's entire existence and its stunning success is a direct result of our species' ability to discover, understand, and most importantly, trust that these constants are, in fact, constant. We have to believe that the universe plays by a consistent set of rules, and everything from the launch pad to the final transmission is a monumental act of faith in that consistency. Consider the role of a few of these pivotal numbers. The speed of light in a vacuum, designated by the letter c, is perhaps the most famous universal constant. Its value is approximately 299,792,458 meters per second, and this value is the ultimate speed limit for the cosmos. But for a deep space navigator, c is far more than just a curiosity. It is the most fundamental measuring stick we possess. When a probe determines its distance from Earth, it does so by measuring the time it takes for a radio signal to make the round trip. This calculation is entirely dependent on knowing the exact value of c. A tiny error in this constant would translate into a massive error in the calculated distance. Every single measurement of range and every calculation of the Doppler shift used to determine velocity relies completely on the unwavering stability of the speed of light. It is the constant that allows us to turn time into space, to use the ticking of a clock to draw a map of the solar system. Then there is the gravitational constant, g, which quantifies the strength of the gravitational force. This is the constant that allows us to write the score for the celestial dance of orbital mechanics. When navigators calculate the exact trajectory for a gravity assist around Jupiter, they are plugging the mass of Jupiter and the value of g into Newton's equations to predict the exact amount of momentum the probe will steal. The entire concept of a Hohmann transfer orbit or a gravitational keyhole is predicated on g being the same at Jupiter as it is here on Earth, and as it was when Isaac Newton first pondered the falling apple. We never send a probe to a planet to measure its gravity for the first time. We send it knowing exactly what the gravity will be because we know g and we have measured the planet's mass from afar. This is the power of a universal constant. It grants the power of prediction across the void. On an even deeper level, we have constants like Planck's constant, h, which lies at the heart of quantum mechanics. While it might seem less directly involved in steering a spacecraft, it is absolutely critical to the function of the technology that makes the journey possible. The lasers in our ranging systems, the precise operation of the star tracker's charge-coupled device sensors that capture photons from distant stars, and even the fundamental physics of the semiconductors in the probe's computer all operate according to the quantum rules defined by Planck's constant. The universe, from the galactic scale down to the subatomic, is woven together by this consistent numerical fabric. This predictability is what transforms the seemingly chaotic and empty void of space into a navigable medium. It's the difference between trying to sail a ship across a stormy, unknown ocean with no charts and no understanding of the winds and currents, versus sailing across a calm, well-mapped sea with predictable tides and steady trade winds. The constants are our chart and our understanding of the cosmic winds. They provide a stable stage upon which the drama of exploration can unfold. Because we know that C and G and H are the same at Pluto as they are in the laboratory, we can project our will across the solar system. We can aim a spacecraft with the confidence that the physics we use to calculate its path here on Earth will hold true throughout its entire journey, that the equations we solved in the comfort of our warm, well-lit offices will remain valid in the cold, dark depths of the Kuiper Belt. This trust in the constancy of nature is the greatest leap of faith in all of science, and it is a faith that has been vindicated with every successful planetary encounter, every perfect orbit insertion, and every stunning image returned from the edge of our celestial neighborhood. And so we arrive at the heart of the matter, the grand synthesis. We have journeyed through a universe of individual pulses, from the unwavering tick of atomic clocks to the predictive power of orbital ephemerides, from the silent thermal regulation to the vigilant heartbeat of fault protection. Each is a masterpiece of engineering in its own right, a specialized instrument playing its own part, but a collection of virtuoso musicians does not make a symphony. The true marvel, the genuine miracle of deep space exploration, is how all these disparate rhythms are woven together into a single, seamless, and breathtakingly coordinated whole. This is where the probe transcends its physical form of metal, wire, and silicon to become something far greater, an intelligent, resilient, and purposeful entity. The maestro of this cosmic orchestra is the probe's main computer, and its baton is the relentless, multi-layered rhythm of its software loops. These are not mere lines of code. They are the cognitive processes of the machine, the structured patterns of thought that allow it to listen, decide, and act as one cohesive being. Imagine the main executive loop as the conductor's steady, underlying beat, the fundamental rhythm of existence that never ceases. With each cycle, this loop performs a comprehensive health check, a constant, low hum of self-awareness that asks, is everything as it should be? It checks power levels, confirms temperatures, and verifies that no subsystem has raised an alarm. Simultaneously, it consults the master mission timeline, a gigantic, pre-composed score of activities, and executes any commands scheduled for that precise millisecond. This is the probe's foundational consciousness, the part of its mind that ensures the basic functions of life are maintained. But while this executive beat provides the steady tempo, numerous other, faster loops are running in parallel, each dedicated to a specific, high-priority task. The attitude control loop, for instance, is a flurry of activity running hundreds of times per second. It is the conductor's precise ear for pitch, constantly listening to the gyroscopes and star trackers, feeling for the slightest uncommanded wobble, and instantly commanding a reaction wheel or thruster to correct it, ensuring the spacecraft's orientation remains perfectly poised. This layered cognitive architecture means the probe is not just doing one thing at a time. It is managing a symphony of simultaneous processes, from the slow, deliberate planning of a trajectory correction weeks in the future to the microsecond-level adjustments needed to keep an antenna locked on a distant, pale blue dot. The magic happens in the integration, the moment these separate loops and their associated sensor data are fused into a single, coherent state of awareness. The computer is not just hearing the individual instruments, it is understanding how they relate to one another, creating a harmonious picture from what would otherwise be a cacophony of data. Consider a routine moment in the life of a probe. Its atomic clock provides the absolute tempo, the unwavering tick that stamps every event with a precise timestamp. The star trackers provide the melodic line, the absolute reference for orientation against the fixed backdrop of the cosmos. The radio link with Earth provides a baseline of ranging data, giving a direct measurement of distance and velocity. And the gyroscopes provide the internal rhythm, the sense of its own motion. The Kalman filter, that brilliant algorithm of refined estimation, acts as the conductor's intuitive sense of harmony. It takes the prediction from the gyroscopes we should be pointing here and blends it with the absolute truth from the star tracker we are actually pointing here to produce a smoothed, accurate, and trustworthy estimate of the probe's true attitude. This same process of synthesis happens for its position, its velocity, its power state, and its thermal condition. The computer builds moment by moment a living, breathing model of itself and its environment, a digital twin that exists within its memory, which is so accurate it can be used to predict the future. This unified awareness is what enables truly intelligent, coordinated action. The probe is not simply reacting to individual stimuli. It is making decisions based on a holistic understanding of its state. For example, the command to execute a scientific observation is not a simple turn on the camera. It is a complex sequence that must be perfectly synchronized across multiple systems. The computer's timeline manager, working from the main executive loop, knows that in 15 minutes it is scheduled to image a specific moon. As the time approaches, it initiates a cascade of preparatory actions. It first checks the power management system to ensure sufficient energy is available for the high-drain camera and its cooling system. It then commands the thermal control system to begin warming the camera's components to their optimal operating temperature, a process that must start minutes in advance. Next, it tasks the attitude control system with calculating the precise maneuver needed to point the camera at the target. This maneuver itself is a synthesis. The system uses the fused attitude data to know its current pointing, consults the Ephemeris to know exactly where the moon will be in 15 minutes, and calculates the most fuel-efficient slew to get there. At the exact moment the thrusters fire, the spacecraft rotates, the camera powers up, and the shutter clicks, capturing a priceless glimpse of an alien world. Every single one of the hidden rhythms we've discussed plays a part in this singular event. The atomic clock timed it, the star trackers confirmed the pointing. The power system delivered the energy, the thermal system kept the instrument healthy, and the fault protection system stood watch, ready to abort the sequence if anything went awry. This is the scientific crescendo, a moment where a machine, acting on its own millions of miles from home, performs a ballet of exquisite precision, all because its countless internal rhythms are synthesized into a single, purposeful will. This synthesis is the ultimate expression of autonomy. It is what allows a probe to not just survive but to thrive in the void. When an unexpected event occurs, a stronger than anticipated puff of solar radiation pressure, a momentary glitch in a sensor, the probe does not falter. Its synthesized awareness allows it to contextualize the anomaly. It can cross-reference the unexpected motion with data from other sensors, determine if it's a real trajectory drift or a sensor error, and decide on the correct course of action, all without ever needing to ask for help. It transforms the spacecraft from a fragile, remote-controlled toy into a resilient, thinking explorer. It is this masterful coordination, this silent, continuous symphony of physics and computation, that breathes life into the machine, granting it the ability to maintain perfect alignment and unwavering purpose across the breathtaking emptiness of interplanetary space, a tiny, intelligent spark of humanity holding its course against the infinite dark. The hidden rhythms that guide autonomous probes are a testament to human ingenuity, turning the chaotic void of space into a navigable medium. From the unwavering tick of atomic clocks to the predictive power of orbital mechanics, these synchronized pulses create a framework for exploration that operates flawlessly across billions of miles and decades of time. These rhythms are the silent partners in our greatest adventures, the unseen forces that keep our robotic ambassadors on course. As we push further into the cosmos, to other stars and their planets, our understanding and implementation of these rhythms will only become more sophisticated. The next time you look up at the night sky, remember the silent, rhythmic dance of exploration happening out there, a symphony of science and engineering written in the language of the universe itself.